Hello friends, so we are at the last topic of convergence in weak convergence, and in this context we have discussed that what is the relation between convergence in probability and weak convergence. We have shown that convergence in probability implies weak convergence or convergence in law, but the converse in general is not true. Now, however, we have this very interesting result that if xn converges in probability to 0, a constant, and then it is equivalent to that xn converging in law to a random variable x, where probability x equal to 0 is 1. Now, the fact that convergence in probability implies weak convergence, so one part of the result is trivial, but to prove the converse part, so suppose we have xn converges in law to x, where probability x equal to 0 is 1, then we are to prove that this xn converges in probability to 0, that is for every epsilon probability mod xn greater than epsilon greater goes to 0 as n tends to infinity. So what is probability mod xn greater than epsilon? This is equal to 1 minus probability that xn is between minus epsilon to plus epsilon, and for any random variable what is that probability? That is fn epsilon minus fn minus epsilon, where fn is the distribution function of xn. Because you remember, for any random variable x, if f is its distribution function, then what is f of b minus f of a? Then that is the probability that x is between a and b. So therefore you have this formula. Now if f is the distribution function of x, then what is probability where x equal to 0 is 1? Then you see that f of y, which is probability x less than equal to y, that is 0 for y negative. Why? Because y does not take any negative values, and f of 0 will be probability x less than equal to 0, that will be 1, because x is taking the value 0 with 1, and similarly for any positive it will also be 1, because below any positive number y, x has only one value, that is 0, and that is probability 1. So you imagine the curve of f, that how does that look like? Then f looks like that it has only one jump discontinuity point as 0. So it is 0 to the left of 0 and it is 1 to the right of 0. So therefore, now why that this is important of relevance to us? Recall that what was the definition of weak convergence or convergence in law? Then it means the first definition was that a fn, which is the distribution function of xn, that has to converge to the f, which is the distribution function of x, at every point where f is continuous. So the convergence need not happen at the discontinuity points, but at every continuity points it has to happen. So in this context, what will it mean? That for every positive number epsilon, so fn epsilon has to go to f epsilon, and fn minus epsilon has to go to f minus epsilon. So therefore you have this result. So if you take the limit, a probability xn limit mod xn greater than epsilon, then that will go to 1 minus, and this will be, again this difference will be 1 minus 0. So the limit is 0. Hence we have this result. So you remember this result very carefully, that although in general convergence in law does not imply convergence in probability. For instance, we had that example, no? Just suppose x is any standard normal random variable, take xn to be minus x. So then you have weak convergence, because all the fn's will be equal to f, because xn and x will both follow the same standard normal distribution, but obviously mod xn minus x will be twice mod x, so that you will not get the convergence in probability. But here we have proved that if in this particular case, that convergence in law to a distribution which is like a constant, so we can loosely say that xn converging in law to 0, that will also not be wrong to say. Then what will happen is you will have the convergence in probability as well. Now the next question is this, in this context related to convergence. So suppose xn is converging weakly to x, and yn is another random variable on the same space which is converging in probability to a constant. And so convergence in probability to a constant means same thing as we have discussed. So this will mean that yn minus c converges in probability to 0. So instead of xn, you imagine yn minus c. So probability mode yn minus c greater than epsilon going to 0. So in this, so xn converges weakly and yn converges in probability and to a constant. Then what happens to this? Then what happens to xn plus yn or xn into yn? The answer is that both these xn into yn converges in law, or in probability converges in law to xn plus c or c into xn, as the case may be. So this is known as the Slutsky's theorem. So in general, you will I am not writing it here formally, you will get it in the Wikipedia. Here is the link. So what it is saying is that xn plus xn and yn are two, what I have said, that two sequences of random variables on the same space. Xn is converging in log, so they are saying in distribution, that is the same thing, and yn is converging in probability to a constant. So then xn plus yn converges in log, converges in distribution to x plus c, xn into yn converges in distribution to x into c, and xn by yn converges in distribution to x by c, provided c is not a constant. So this is the Slutsky's theorem, and it has many it is often used in problem solving, in when you are proving weak convergence or convergence in law. So here the important thing to note is that here we need convergence to a constant, because if you replace it by yn converging into probability to some random variable, then this result need not hold. And in this context, an example is also given here. So suppose xn's follow, all xn's follow uniform distribution on 0, 1 and yn equal to minus xn. So xn plus yn is 0. So here xn plus yn is converging in almost surely in probability, in law, in every sense to 0, because xn plus yn is in 0. But if you add up what are the limiting random variables, so you see that minus yn will follow a uniform distribution on minus 1 and 0. So the in that sense the limiting distribution, so xn plus yn is 0. Now this does not converge to the distribution of the sum of two random variables, where one is uniform on 0, 1 and the other is uniform on minus 1 to 0. So therefore you do not have this weak convergence here. So xn plus yn does not converge in law to the distribution of x plus y. That does not happen in general. So this theorem is mighty useful, Slutsky's theorem, but only when convergence of the convergence in probabilities to a constant. So here is an example. So suppose I have got IID random variable, mean 0, variance finite. Then I am asking you, what is 1 by n to the power 0.6 x1 plus x2 plus xn. Now apparently this is a tricky question, because if I would have asked you what is 1 by n, so 0.6 or type, if I would have simply written n, then what is the answer? Then you know this converges in probability to 0. This follows from law of large number or the weak law of large numbers. If I would have written 0.5, then what would have been your answer? 0.5 hole, then you know that this is square root of n, and then by central limit theorem this will converge in law to normal distribution, standard normal distribution. But I am not saying 1 or 0.5, I am saying 0.6. So this is a number between 0.5 and 1. So what is the limit of this ratio? That is my question. So now you see, I can look at it as how? I can look at it, this ratio you can think of a product. What kind of product? Paste. So here you can write it 0.5. Kintu yat 0.5 likhile something remains. What is that something? That's the other thing is thing raised to the power 0.1. So you see, this part we know. This part by this is square root of n 1 x1 plus x2 plus xn. This converges in law to standard normal distribution. So you have this you can think of xn. So this is converging in law to x, where x follows n01. But if you take yn equal to 1 by n to the power 0.1, so this is going to 0, right? This is going to 0, so it will go to 0. Obviously ynw is equal to 1 by n to the power anything positive, that will go to 0 almost surely, and hence improbability. So therefore by Slutsky's theorem applies here, because the yns are going to this is my yn, so this is going to 0 in almost surely, and also that means in probability to a constant 0. So the product will be, it will converge in law to 0 into x, where x is a normal random variable, so that is 0. So it is so this is converging in law to 0, and so by this lemma we can say that this is converging in probability to 0. So this is an example, and then there are many cases where you want to prove that something is going to converging in law to standard normal distribution, but you can express it as a sum of xn plus yn, and it is easier to prove that xn is converging in law to n01 and yn is converging in probability to 0. Then and by Slutsky's you get that xn plus yn is going converging in probability to standard normal distribution. So this is a very useful theorem, and often used frequently in problem solving. So thank you.